Can you see the screen? Okay. So today we are discussing on RNNs. So I think before we solve, I want to quickly recap right? What is RNN? Why do we need it? And how it is different from fully connected layers and CNNs that we discussed last week. Um, okay, so yeah, so this is the structure of RNN. Right? This is called as recurrent neural network, and so here. I have given one application of RNN. So, I mean, typically this is called as many to one. Many to one in the sense you have many inputs and single output. What is a typical example of such a this thing is your recommendation systems, right? Or movie reviews. Somebody writes a movie review and you want to rate it between 0 to 5, 1 to 5, whatever. Right? So that review sentence is your X1, X2, X3, and that is the rating that you give is captured by Y. So that is many to one. Another application is many to many, where you would like to convert one language to another language. Right, so maybe French to English or Hindi to English or whatever, right? So that is one application. So I just pointed out one application here. So don't get confused that RNN is used only for these kind of things, right? So it is a general thing. People use it for time series forecasting, etc., etc. A lot of things. Anything where there is a sequential data, RNN can be used. Okay, so this is the form of RNN. All right, so you start with some hidden state that can be zero or some random this thing, right? And you feed your input. So one thing, right? This input typically is a text when you are dealing with NLP, natural language application. How do you convert this to? How can this take numbers? You know what is this thing? Already we discussed 1 week before that. So what you do is word embeddings, right? To have this glow or some other word embedding, word to wake, right? You pass this word to this word embeddings and get the vectors. Vector, I mean the real number representation of that word. Okay. So when I say x1 in the context of sentence, that is what x1 means. It is the mapping of words to this thing, the vector in of real numbers through some word to vec or something. Hmm, just give me a second. Let me disconnect my. Can you hear now? Can you hear me now? Can you hear me now? Okay. Yeah. So what I was saying is the same. Right. This architecture is used for many to one application. I mean, and RNN can be used wherever there is a sequence data. Okay, so I just picked up one application where the architecture uses many to one, and the typical application is any rating, right? And review, right? Where you say movie rating, right? You talk some text about it, and you want to rate it from 0 to 5 or 1 to 5, whatever, and you just do it. Okay. Uh, can you guys hear me? Can you guys hear me? Yes, sir. Okay, okay. Uh, right. So what is that? What is this box actually? So I am writing www. What is this box actually? This box is, I mean, to be specific in this equation, I mean, if I want to map this W, right? It can typically represent your this thing Wx and Wh. Okay, this can parameterize both and write it as W in this box. So what is the actual dynamic that is going on here is your HT is tan H times your Wx times XT and WH times HT minus 1 plus some bias, right? It's just a linear combination of your input and with the weight vector Wx, right? Linear combination of your previous hidden state and your weight vector Wh and some bias B. You apply a non-linearity on top of that. That's it. And you don't know what is Wx and Wh. You will learn them from the data. And remember, this is typically called as time steps, x1, x2, x3, and so on. And at every time step, this W is same. It doesn't change. Okay, that is important, right? So finally, once you learn everything from x1 to so on xt, some time steps, right? Finally want to predict, say that is whatever rating, movie review rating, right? So finally you do a soft max on this final this thing hidden state. You take a linear combination, probably a bias as well, but I'm just ignoring it. You just take softmax and try to do cross entropy loss with the ground truth. This is y hat. Let's say ground truth review is something, and you just do cross entropy loss of y hat and y. So does anyone know what are the problems associated with this simple RNNs? You want me to go over, or we can skip and go to just quickly LSTMs and GRUs? Yes, no, no, anything. Okay. So basically RNN is that's whatever I said, that is RNN, right? So now what are the problems with this simple RNN, right? So thing is, if I want to make a gradient update on say W, weight W, okay. Um and I have this H1, H2, and so on HT, right? If I put T as some 100, okay. So thing is, this Y is coming after 100 steps. And if I want to do a back propagation on W, I need to go back and find the change, the impact of the change in with respect to W till the first time step, right? So you have to come back all the way from 100 to almost to first time step. So what happens during this is this term typically, right? When we compute this dou ht by dou ht minus 1, right? And then dou ht minus 1 times your whatever w. And this is say on the last time step, right? And you keep doing this. So what happens is this term keeps getting multiplied. So what happens is you end up getting terms WH, some raised for some big number. So this is number of time steps, let us say. So it again it boils down to this thing, right? How well your W is conditioned. Right? That typically that you don't have things in control because it depends on data. Right? So if this W is very small, right, you don't have this dependencies. Basically, what happens is your output is agnostic to your inputs, right? Initial part of input, because information is lost till you come back to that point, right? So that this is called as a vanishing gradient problem. This is seen with simple RNNs, and this is overcome using little bit more sophisticated architecture such as LSTMs and RNN, sorry, GRUs. Okay, so let's go to this thing. LSTMs and GRUs, right? Okay, so this is LSTM. So what happens in LSTMs is you have these gates. Basically, these are the crucial updates. Uh, so there you had only one HT that is propagating from one cell to other cell, right? So here you have two um, states, cell state and hidden state, that keeps propagating from your one state to another state. So this is T minus one. Okay. So this thing, this CT minus one, addition of this CT minus one allows the gradient to propagate from the farther to the initial part of your sentence or sequence, right? So I mean this having this cell state helps dealing with the vanishing gradient problem. That's a very high level explanation. Um, right. So I mean, LSTM was introduced as to solve the problem introduced by this thing RNN. This is another uh, popular technique called as gated recurrent unit. Um, this is a little bit lightweight than LSTM, but it does eventually it does the same thing. Um, okay, so this is at least this much background I want to give to you before solving the problems. Okay. And one more thing, one more question. Say let's go to this thing. Um, Now, if I let us say train all my sequences x1, x2, x3 with say the length of in my training time, if my length of the sequence, if I see a length 30 till x30, I mean the words or sentences, if I take only 30 words, sentences containing 30 words. If at the test time, if my sentence comes with 35 words, will it able to handle? This is training. If at test time, if I end up seeing a 35 length sequence, will this architecture able to handle? Yes or no? Variable length sequence can RNN handle? I mean, you can see, right? I mean, all you are learning is WX and WH, and it is independent of the length of the sequence, right? I mean, You have, say you have initial x1 comes here, you use wx wh throughout h1, and again you put x2 here, use same wx wh, and you can keep repeating this. So RNNs can handle a variable length inputs, unlike your fully connected neural networks, right? If you change the input dimension, input length, it will not work. Okay. You understood? You want me to repeat what I just said? Okay, then. So let's solve the problems. Okay, so which of the following is a limitation of traditional feed-forward neural network in handling sequential data? Um, they can only process fixed length input sequences. Yes, that is true. Your input dimension is fixed in full feed-forward neural network. Um, I mean, they cannot handle variable length input sequences, and they can't model, definitely, they cannot model temporal dependencies between sequential data, right? And they are not impacted by the order of input sequences. Okay. Any questions on this first part? Question. Can go to second. Yeah, which of the following is a common architecture used in this?
Whether it is optimizable, sir?
Which one?
Previous question.
What do you mean by optimizable?
Optimization techniques, whether the optimization algorithm, whether it can be applied for it.
Yeah. There's nothing special about uh, RNNs from the optimization point of view. And at the end of the day, you will have a loss function that is parameterized by some W's. WX in this context, it is WX and WH. Okay, so the whatever I have given you, right? So I just said that if you are doing the many to one, such as sentiment prediction of or whatever, uh, you are doing some movie review, this thing, right? You have y hat as what you predict. Y is your ground truth data, and you do a cross entropy loss of y and y hat. Now, y hat, remember, is a function of your wx and wh only, okay, which I have written as w. And what form your loss function takes is up to you, right? If you use fully connected neural networks, it end up doing something. If you use RNN, it is you will do something, right? So it is perfectly optimizable to answer
Oh,
your question in the first place.
okay.
Okay, so let's go second. Which of the following common architecture used for sequence learning in deep learning? CNNs, no. Autoencoders, no. RNNs, yes. GANs, no. Okay. This is simple. If someone replaces autoencoders with LSTMs, you have to choose both. And if someone replaces, say, GANs with the transformers, you have to choose that as well. I'm not sure transformers we will discuss or not, but yeah, I think attention we will definitely discuss next week. So by the way, there is will be one extra session where we can have where you can ask questions from whatever we have discussed throughout the syllabus. Right. I mean, even I'll pick some of the problems and solve. But yeah, there will be one session where you can, after the 12th week, we'll have one session. Okay. That those details I think you will get. So what is the vanishing gradient problem in training RNN? So just now I explained it, right? Why it comes, through which way it comes, right? So basically, the gradients of weight updates will become very small. Why it becomes very small is this because of this WH, not because of WX. You have to be very careful, right? So this thing, this chain, dou ht minus one, what happens is dou ht minus one by dou ht minus two, right? So this there will be a chain of derivatives. So what you have is you end up having a term something like this WH power the number of steps. So T, if T is 100 and your WH is not well conditioned, it's gone. This will become zero. Okay, so that's why your gradients become too small. Yeah, which of the following is main disadvantage of back propagation through time? BPTT that's what back propagation through time. It is very computationally expensive. I mean, in general, anything is computationally expensive. I mean, it is too. I mean, relatively, you should answer. You need to be careful because if someone, if there can be many other methods that can be computationally expensive than BPTT, but yeah, in this given options, that is most relevant answer. It's not difficult to implement because it is very easy. You just need to store WX, WH, that's all. And it is independent of the data. It is prone to overfitting. So there's a very, very general statement. Anything is prone to overfitting depending on the data, right? Yeah, you pick whatever is the most appropriate. Okay, so what is the typical sequence of the order we perform this LSTM is you have to selectively read and then selectively forget and selectively write. So basically, just a fancy way of telling whatever we have just discussed. Okay. So this is my input, right? This is called as reading XT from your input. Okay. This step IFOG, this is reading your inputs, right? And second, what this said was selectively forget. Okay. What was it? Yeah. So now after reading this, all these things, you forget, you apply this thing, right? Selectively forget. Um, from your previous cell state. Then you will write into cell state. That is what it is. That's what it means. I mean, this is a fancy way of telling whatever we have done in these equations. Yeah, what are the problems in RNN architecture? Morphing of information stored at each time step. That is true because each time step you compute your uh, hidden vector based on that input, right? So that's what it is. Exploding and vanishing gradient problem. Okay, so far I have discussed vanishing gradient problem. Right now I haven't mentioned what was exploding. It's also the same thing. um Say WH, if the values are too small in WH, it end up going to zero. If WH the values are too high, right, it will blow up. This will become, say, infinity. I'm exaggerating infinity, but it will become too high. So if it becomes too high, typically your processors, it has a fixed precision, whatever 32-bit or whatever, right? Numbers becomes too high, it saturates. And that's a exploding gradient problem. The other is exactly opposite of vanishing gradient. This can also happen in RNNs. But typically, what happens is, in general, we take care of this exploding gradients by putting a threshold on the gradients. Say, okay, if my gradient, if I compute a norm on my gradient, if my norm is more than 10, I would saturate it to 10. Typically, that's not a serious problem compared to vanishing because we use these techniques to prevent it. Okay, so that is what it is. I mean, yeah. And error caused at time step can't be related to prime step, previous time steps far away. Exactly. So that's what I said. Right. If there is some loss that has happened here because of vanishing gradient problems, it cannot be back propagated through the initial steps. This happens because of vanishing gradient problem. I mean, this statement is because of vanishing gradient problem. Yeah, what is the purpose of forget? gate in LSTM network, just simple. It is to decide how much cell state to keep. Um, you just have to know these equations to understand to answer this, right? So forget this is forget gate. This allows how much cell state information to be propagated into the current uh, step. And yeah, what is the following form? Which of the following is the correct formula? This is the right thing. To compute. So one simple way to remember this is whenever there is a gate, so the activation typically used is sigmoid, not tanh. This whenever you see gate, this option you should be immediately able to discard. This is the most appropriate one because it has bias. Okay, so next two questions are based on this architecture, same thing that we have shown. Your input layer, you are getting a sequences here. And yeah, so your hidden layer has the dimension of 4, and your output is each at each time step you have. Okay, at each time step, your output is a vector of 3. So, how many neurons are in the hidden layer at state S2 of RNN? And this is very, very simple question. What is asking is here my hidden layer size is 4 that is given. What is the hidden layer size here? It will be same. Hidden layer dimension is same throughout the network. Okay. Your input dimension will be same throughout the network. Length of the input changes, but input dimension is same. Another question. We train this RNN and it has learned some weights. And let's say it has associated a weight x1 x1 to h1, this weight, this edge weight, it has learned to be 3 at S5. Right? At step 5, let us say this is step 5, it has learned this weight to be 3. What is the weight at S step 6? It will be same because the weights at each time step are the same weights, right? We are not saying that at time step 1 I'm using some W1, time step 2 W2. No, at every time step we are using same weights. Okay, so I think that's all I have for today. May stop recording.